Hello and welcome, this is Manuel with Entagma, and I'm here with a new Geometry Nodes tutorial for Blender. Today I want to talk about noise advection. I want to advect some points through a noise field. That is a quite handy operation because it allows for visualizing a noise field, and on the other hand it creates some beautiful graphics, so it is handy in this regard too. The big problem with coming up with an algorithm for this is that Geometry Nodes unfortunately does not support loops yet, and it does not support simulation. As you will see in a second, we will need some sort of looping to move our points through the noise field, but we will find a workaround, although it might be a little cumbersome. But now let's dive into Blender and follow me implementing noise advection inside of Geometry Nodes. So to start, let's get rid of the camera. We won't need it for now, and the light, we can add them in later, and split the view to create a Geometry Nodes viewport. And let's select this cube. It really doesn't matter which geometry to choose. We will overwrite the geometry anyways, and let's create a new Geometry Nodes tree. Let me get rid of the N panel, and here we have the group input and the group output. First, let's cut this connection, making the geometry disappear. Now, we want to start with a line, and I want to use a curve line because a curve line allows me to later on define how many points the line is composed of. So let's start with this curve line. If we connect it here, you see we get a line in the viewport. And now let's create a resample curve node. And this node allows us to specify how many points are used for this curve. So now we have 10 points. We want to move these points through a noise field, and that means we need a noise field first. So let's create a noise texture. This creates a noise field, and it outputs either just a float value or a vector in form of a color. So what we could do now is we could just lay down a set position node, set position, and if we connect it here, we can now move the points around using this offset, as you can see. And if we just connect this color to this offset, we are effectively moving the points using the vectors from the noise field. So now every point samples a vector at the position where it is in the noise field, and then this vector is used to move the points. But we have some problems here. First, all the points are moved to the first quadrant, and that is because this noise texture spits out values between 0 and 1 only, because it is colors. So first we have to transform these values to be centered around the origin. And to do this, let's use a map range node. So let's lay down a map range node. But before we continue, let's switch this over to vector, because we are intending to remap vectors. Connect the color here. And now let's remap the ranges from 0 to 1 to -1. to 1. Now we are centering the value range around the origin. If we are using these values, you can see that we now centered the deformation effect around the origin. But still, this is not what we are after. At the moment, I am transforming every point with a vector at the location where the point started. What I want to do instead is I want to start with the very first point and then travel through the noise field. So the very first point should stay at 0. Then we want to read the value of the vector at this location and move the next point to this location. Then we want to sample the position here and move the second point to this location. And so on and so forth, moving the point of the curve through the noise field. But that means we have to accumulate the vectors. So the first point samples the first vector, and then the second point is moved to this location, and all the other points too. And then they are moved from this location to the next location, and so on and so forth. So this approach does not get us anywhere, so let's cut this connection. Instead, we want to move them successively. First, we want to put all the points just at the origin to start. So let's go into this curve line and move all the points to 0. We are still having 10 points, but they are all cramped into the origin. And now we want to sample the first vector position for all the points at this location. But we only want to set them to all the points but the very first one. So we have to use this selection of the set position node. To tell the set position node to only set the values for all the points but the very first one, we can use a compare node. So let's lay down a compare, and we want to compare integers because we want to compare indices. For this I need an index node, spitting out the indices of the points, and I connect it here. And I can tell this node to only output true if the index of the point that is currently processed is greater than 0. And that is true for all the points but the very first one. So now if I connect this here, and connect now my vector from the noise texture to the offset, you see that all the points are moved a little bit, but the very first one. Now from here we can sample the next noise vector, and then move all the points points further through the noise field. To do this, because we do not have loops unfortunately, we have to replicate this set position setup by hand. So let's select these two nodes and duplicate them. So after the first set position, let's create a second set position like so. And we want to again move the points around. But this time we want to move all the points but point 0 and 1. So the first 2 points should stay in place, or the others should move to the next location. So let's put in 1 here. All the points greater than 1 are now moved. Now before we continue with this process, because we have to add more and more of this set position nodes for all the points that we have on the curve, let's first change the settings on our texture, because the noise texture at the moment has a scale of 5, and that means we have a lot of detail in here. Let's go down to 1 with a scale, and maybe we want the opportunity to move the noise field through space. So let's create a vector mass node and set it to add. And now let's create an explicit position node, because if you do not connect anything to this vector port, it implicitly connects an invisible position node to this vector. We want to do this explicitly, so let's create a position node and connect this to this add here. And that allows us to specify a second vector to move this noise field around. And you can see it is working now. The first 2 points are moving through the noise field, one at a time. Now to make the entire spline move through the noise field, we can continue with this process. Now let's select both of these setups and duplicate them, and let's connect them here after the first 2 set positions, like so. And now we have to connect all the vectors to the offsets, like here and here, and we have to connect all the indices to the A ports of the compares, and we have to, of course, change the numbers, because now with this third set position, we want to set all the points but 0, 1, and 2. So let's put 2 in here. And with this one, we put 3 in here. And you can see now the points are successively moving through the noise field. That is what I am after. The problem is that the vectors that this Perlin noise outputs are not necessarily always of the same length. So let's make them the same length, because we want to decide the step size through the noise field. So let's take all of this business and move it to the left, and maybe let's introduce a new reroute to make it easier for us. And now let's lay down another vector mass and switch this to normalize. Normalize will make all the vectors that come out of this map range a length of 1. And now that we have vectors that have always a length of 1, we can just duplicate this node, set it to multiply, and decide how long the vectors will be by multiplying them. It is convenient to create a value node, value, and connect it here, such that we can set all the 3 components of the vector here with just 1 value. And maybe we want to rename this node to make sure that we remember what this is for, and call it step length, because this value decides on how large a step will be. Now with this in place, we can connect this here. And with 0, we don't get any result, but if we increase this value, you see, you can decide how long a step through the texture field will be. Let's say 0.1 for now. Now we have a little spline here crawling through the vector field, and to make it longer, remember that we have 10 points, we need to add another 6 iterations by hand until Geometry Nodes finally implements loops. So let's copy all of these and move them over here and connect them in, and don't forget to connect all the vectors. That is why this reroute is handy. I can temporarily move it over here and easily connect all these offsets like so. And then we want to connect all the indices to the comparison nodes, 1, 2, 3, and 4, like so. And we want to dial in the numbers. So we ended at 3, so this will be 4, and this will be 5, and this will be 6, like so, and this will be 7. And now our spline got longer, because we now take 8 steps through the vector field. Let's move the vector field around to see what happens. And you can see I can move the vector field around, and the little curve just advect through the vector field. So 2 points left, because we have 10 points with the curve. So we have to create 2 more iterations by hand by duplicating these, and now connect them in. and connect everything up. First the offsets here, and then the indices. I will temporarily move my index node down there for easy connection, like so. Connect, and put in the numbers 8 and 9. And now we have 10 points moving through our vector field. So that is the basics of what we wanted to achieve. We can now make the vector field move, and the points on the spline are advected through the field. That is great. But what if we want to use more points? In this case, we would have to create even more iterations, and that is cumbersome. So why don't we just turn these 10 iterations into a group that can be reused easily? That is what I want to do next. But to do this, I have to make sure that the numbers are not hard-coded. Instead, I want to come up with a logic for these numbers. And this logic is not hard to create because it is just adding up 1 to each number. So let's move these connections out of the way, and instead of putting in these numbers by hand, let's create a mass node to do it, like so. Let's assume we have a start value of 0, and now we want to add to this value of 0 1, like so, and put this here. This gives 1, so this is now a 1. And now we can duplicate this add and just add 1 to the result of this and use it here. And let's continue the process, add another one and use it here, and another one and use it here. And now we can copy all 4 nodes, move them over, and again wire this into there, and that into here, and this into here, like so. This goes there, and this goes there, and one more. So duplicate, add 1, and put it here. Now we procedurally created all of these numbers. Now that we have that, we can, in theory, create a group out of all of this business and reuse the group. So to do this, let's introduce another reroute just to make sure that we only get 1 input port on our group. Select everything and make sure to select these 2 reroutes too, and then go to node and make group. This puts all of this business into a group. If we leave the group, you see now we have a nice group node. I will call this node ent for Intagma _ advect. That is what the node does, and then 10 to indicate that this is doing 10 advection steps. And now we have a very clean setup again because we only have this one node. If we go inside, we have 3 automatically created input values, geometry, offset, and A. Let's deal with this by bringing on the N panel, and if we go to group, we can rename the ports. So offset is okay, and A is just the index, so I will call it index. And we will need the start value, because at the moment the start value is 0, that is nice. But if I want to make more iterations, I probably want to start at 10 or something. So we need another port here. So let's drag from this port to this value, and let's call this newly created value start value, or start index is probably even better. Start index, and let's make it an integer, like so. Now we can leave the node, and we see we have this start index here. And that means that we now, in theory, can create more points on the curve and then use many of these advect nodes in a row to make 10 advections at a time. This way, we can fake iterations, although we don't have them inside of geometry nodes. So first, let's increase the count of the points of the line. So let's go to the line, and let's say we want to do 20 points. So increase this to 20. And now that we have 20, nothing happens because we are only advecting 10. We can duplicate this node and connect it here. Then make sure that it has the noise field and the index. And now we can go with the start index to 10. And now the entire spline advects through the noise field. So if I change this value here to move the noise field around, you can see we are happily advecting 20 points through the field. So why don't we do even more? Because then the spline gets longer, and that is a good thing to have. So let's go to 50 points, and let's just duplicate our iteration 3 more times, like so, effectively creating 50 iterations for 50 points. Connect everything up, and before it will start to work, we have to first give every node the noise field, like so, and every node needs the index, and index, and now we want to start at 20, at 30, and at 40. And now we have a spline traveling through the noise field with 50 points. So we faked an iteration of 50 points, and you see, if you move around the noise field, the spline advects through the noise field. So basically, the spline goes through the noise field and follows the vectors of the vector field and shows you the path through the noise field. To make it more even, let's go down with the detail to 0, like so, and let's probably go down with the step length to 0.05, like so, not too long. And now you can see I can move my noise around and the spline will advect through the noise field. Very nice. But to actually see the noise field, we cannot just use one spline. We need more splines. So why not creating a field of splines and advect all of them? To create a field of splines, it is probably a good idea to use a grid. So instead of just using one spline, let's first lay down a grid, and this grid should get 10 points. And now let me use instancing to put this curve on all of the points. So lay down an instance on points node. And we want to use the grid points as targets and the curves as instances. Before I connect this up, let's quickly look at what we got so far. So if I connect this here, you see that you see nothing. And that is because, remember, the curve line creates all the points at the origin. But if it temporarily create a 1 here, you see we are getting a field of curves. So back to 0. The curves are still there. It's just that they are all moved to 0. And then before we want to use our advection with all of these splines, we have to make sure to prepare them accordingly. First, after the instance on points, the curves are instances. And the points of instances cannot be altered. So let's put down a realize instance node, creating geometry out of the instances. By the way, you can watch this process. If you go to the spreadsheet here, you see we have 100 instances at the moment. And as soon as I introduce this realize instance node, I don't have any instances anymore. Instead, I get real splines with points, control points, many control points, 5,000. Okay, now we have a lot of points, but the problem is that the indices now are all over the place. They are just counting. That means we have indices with very high numbers. But our setup relies on indices between 0 and 50. So we have to make sure that our indices are between 0 and 50. So let's introduce a new math operation to turn our indices between 0 and 50. And this math operation, you guessed it, is called modulo. Modulo gives you the remainder of a division. So if we divide the index number by 50, but then just keep the remainder, we will effectively get indices that go from 0 to 49 and then again back to 0. And that is exactly what we want for advection. So let's put down a math operation, math, and set this to modulo. And make sure to put the same value in here that you used for the count. And now we can create another reroute and put the modulo here. Now we will make sure that all our indices are going through this modulo, effectively turning them in ranges between 0 and 49, and then again 0 and 49, and then again 0 and 49. That means that this loop here will work for all the points at the same time because they get the same indices. Now that I have that, I can just take the Spline Bundle here and connect it here to our output. And don't forget to connect this to the group output again. And you see, beautiful, now all 10 splines are being advected through the noise field. This starts to look quite interesting immediately. So let's see what happens if I move the noise field around. And you can see now the splines are advecting through the noise field, creating a visualization of the noise field and looking pretty at the same time. So that is nice, but what if we would turn this grid into a cube, into a volume of points? Then the visualization would be even more precise. So why don't we do that? Doing this is quite easy. It's just that we don't want to use the grid itself alone. Instead, we want to create a mesh line, and this mesh line should be set to endpoints. And the first endpoint should be minus 0.5 in Z, and the next endpoint 0.5 in Z, creating a line of length 1 centered around the origin. Now I can use this mesh and another instance on points node to instance our grid to this mesh line, creating 10 grids. Let me visualize this for you to better see what we are doing here. You see, now we get 10. And again, we will need a realize instances node because we want to use the points of these grids. So put in a realize instance node. And now let's connect this to the points here and move the output back to the very end of our graph. And you see, now you get quite some advection because we are starting with a grid of points, a cubic grid of points, and all of these points get advected. And that looks quite nice. Let me move through the noise field. You see how pretty this is. how intricate the structures are that are emerging from this operation. Really funny. Okay, but all the splines are just black. That is not that pretty. So why don't we first turn all these curves into real geometry? Let me move the spreadsheet out of the way and let's create a little more room here because now we want to work with the spline themselves. So let's, at the very end, create a curve to mesh node, which will sweep another curve along these curves, and this other curve for now is just a circle, so a curve circle. We don't need a resolution of 32, let's use 8, and make the radius quite a bit smaller, say 0.01, and now connect this here. And now this creates mesh curves. Look at this. Look how funny this looks with all these curves being advected through the noise field. Now this is great, but I would like to not only create geometry, but at the same time color. How could I color this? Well, we started with colors in the first place, remember? We used the colors from the noise to be vectors that are used to move stuff around in space, but we can at the same time use them as colors. So let's set up point colors. For this, I first need a color output port. So let's, for now, create a color node. Let's create some pinkish color and connect it here to this color port. Now we want to set this attribute to the geometry for the shader being able to read the attribute. To do this, we have to go to the modifier, and under output attributes, we now have this color output port. And we have to decide how to name the attribute that is being written to the geometry. I will call it CD because that is what I am used to from Houdini. Color diffuse, that is my color attribute. Now we want to create a shader that can use this attribute, so let's quickly switch to the shader editor and create a new shader. We already have one. So let's create a new attribute node, and let's put in CD. That is the attribute we want to use, and connect it to the base color, and make sure to switch over to viewport shading, otherwise you won't see the colors. Well, at the moment, this is not working yet because we did not apply the material to the geometry. Remember, inside of geometry nodes, materials are no longer applied to the object because we are replacing the geometry of the object. This is not working. So we need a set material node to tell the newly created geometry to accept the material. So lay down a set material node, set material, put it at the very end. And now if we go in here, we can select our created material. And now this connection is working because now the geometry is using the material called material. By the way, let's call it visualize CD. That's a more descriptive name. And the attribute gets written to the geometry. The shader is reading the attribute. The shader is applied to the geometry, and thus we can specify the color from here. But I wanted to sample the colors from the noise instead of just using one color here. So in theory, I could just go in and drag the color output of the noise all the way over to this port here, but this creates a strange noise pattern, and that is not what I want. I don't want to sample the noise after the fact, so all the points of these mesh lines should not sample the noise, and that is what's happening here, and that is why you get these splotches of color. Instead, I want to sample the noise at the origin of each line. So the original points should sample the noise and then color the entire line with this color. To do this, we need a node that tells geometry nodes where to execute this color field here. At the moment, it is executed in this context. So the geometry port on the group output determines the context that the connected field, in our case this noise texture, is executed in. And because we have all the points here, the noise field is executed for all the points. We want to execute the noise field for all the points before we put the curves on them. So for the original points of these cloned grids here. And we can tell geometry nodes to execute this in this context by using the capture attribute node. It is there for this purpose. So if you connect it here, it will allow you to sample the noise field here and then pass on the values to the created meshes. So let's switch this over to be a color of domain point. And now let's connect this color here. Now this node here tells the noise texture to sample only where these points are that are in this geometry input port. And that is the original point. And now this attribute is stored on these points. And if we connect this to the very output at the end, you can see that this changes the behavior quite a bit, because now it only captures the value at the origin point of each spline and then copies this value to the entire curve, giving the curve one solid color. Now, this is pretty much it, but the colors are very, very light, I think. So why don't we use just another map range node to make the colors a little bit more vibrant? Let's duplicate this. The lightness of the colors, the low saturation of the colors, originates from the fact that the values of the noise texture originally are not only between 0 and 1, but usually they are in a range between 0.25 and 0.7 or something. So that is why they are also light. So let's put this color into this map range. And of course, you can put a color into a vector map range because the color is just a vector. And let's say we want to output values between 0 and 1, because this is now meant to be colors. But the input values should be something like, say, 0.35 and 0.7 or so to actively compress the value range. And if we now connect this output to our color, you can see that we get more vibrant colors. And if you ask me, this looks a lot nicer. So look what we created. A very, very pretty vector field that picks up the color, colors everything with this color, and advects the spline through the noise field. And by changing this add here, you can move through the noise field and display different parts of the noise field with color. And look what interesting the shapes are that you can generate with this method. But not only that, being interesting, at the same time, this gives you a very nice indication about how the noise field, the vector field, actually looks like that you are working with. So if you don't want to use this to create some pretty graphics, why don't you just use this for debugging your other setups that may use noise fields? Okay, now to finish this up, let's quickly go to the shader again and finally to rendering. And now let's introduce first a black background. A black background is well suited for this. Now we want to introduce light. So light, point light, give this a little more wattage, say 1000, like so, and move this out of the way. Why don't we just go with a HDR? Let me quickly switch to the asset browser where I have some environments loaded, and I will take this old industrial hall environment that I downloaded from SIBL. You can see now this is pretty. And maybe let's return to the shader editor. Now go into the object shader. I have to select the object, and maybe we want to switch this to Christensen Burley, turn up subsurface a little and connect this color to the subsurface too. Always gives a nice effect to have a little subsurface with Eevee. So let's see what this gives. And this already looks quite nice. And now maybe let's create a seamless background by just introducing a plane and scaling it a little bigger. Let's go into edit mode and just extrude this backside here, move it up. And if I now bevel this like so, let me introduce a few more subdivisions, make it a nice bevel like say so. That looks nice. Let's shade this smooth and move all of this business down a little, and maybe we want to scale it even further. Let's see how this looks. Now this looks really interesting if you ask me. Now we can put in a camera, and let's look through the camera by pressing 0 on the numpad, make the camera viewport bigger, and now lock camera to view to find a nice camera angle like so. And now you can return to the geometry nodes editor. And to animate this, we can just move the noise field around, as you can see. And of course, we could keyframe this value, but I prefer to do it procedurally. So why don't we just lay down a time node, scene time, and let's use the seconds here. If I connect this, it's probably not a good idea because now everything is very quick. But we can, of course, use a combine XYZ to manually create the vector that we want to use. And let's use the seconds only on the X. Now it moves from front to back. Better to use it on the Y, like so. Now this is nice. Still too fast for my liking, so let's put down a math node. And let's just multiply this down 0.5 maybe. This is nice. And because this is all procedural, I can go in and maybe just create less splines to make it evaluate faster. We could of course change these vertices of the grid, but then we have to change this count too. So why don't we just lay down another integer node and connect it here and here and here, such that we can set all these values at the same time. And let's go down to 5, creating a cube made out of 5 sample points. in each direction. Okay, that's great. Last but not least, let's go in and let's go to node and let's call this count, because that is what it is. And now you have a pretty animation of your vector field traveling through your sample grid. So the vector field is traveling through the grid and the splines are advected through the grid, and this gives this interesting animation. And let's see what happens if we go up to 20 with count. That gives quite some splines, but look how pretty this is. And if you move around in time, you are sampling different portions of the vector field, of the noise field. And this, of course, gives different interesting results with different interesting colors. And this is really a nice procedural playground to come up with interesting abstracted forms. Of course, you can go in and change the other parameters of the procedural setup that we just created. So you can, of course, change the step length, make it longer, say 0.1 again, and the splines will be advected longer through the noise. Or you can go smaller, 0.03, and it won't be as long. So that concludes how you create noise advection with curves inside of geometry nodes inside of Blender. I hope you like the tutorial and I hope you find this setup useful for one of your projects. Thanks for listening, and it is cheers and goodbye. If you like what we are doing, please consider becoming a Patreon. Not only for supporting Entagma, but for access to in-depth courses on topics such as particles, vellum, geometry nodes, and so on and so forth. And at this point, let me say thank you so much to all our existing Patreons. Without you, this channel would not be possible. Thank you.